Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we have two problems to do, right? Which one do you want to do first? Anybody has a solution for any one of them? Not you. Yeah.
So the last one, cost function.
This one, okay, let's do this one, probably easier. Okay, so remember, we were doing uncapacitated facility location. Okay, remember what the problem is. We have a bipartite graph. Let's just think of it this way. Between facilities and clients or demands. Okay. Okay, and on every edge in this complete bipartite graph, there is a cost for going from client I to facility F. Okay, so let's just call it distance, DIF. Okay, and for every facility, there is a cost of opening that facility. Okay, and we have to find a minimum cost set of facilities to open. Okay, so once we open a set of facilities, let's say this guy and this guy, then actually the way to assign the clients to the facilities is straightforward, right? Because we want to minimize the total cost. So for every client, you will check which of the open facilities is closest to it, and you will just go to that closest guy. Okay? So the problem really boils down to just figuring out which set of facilities to open, and what I'm minimizing is cost of facilities over F open. Okay? So actually, let's write it a little more formally. Okay? Pick a subset of facilities O, right, such to minimize right, plus for every client, right, you minimize the distance from J to the closest open facility. Okay, so this is just short form for min over O of dj comma f. Okay, so this is the problem, right? Okay, all right. And so I want and the reason it's called uncapacitated is because I'm not putting a restriction on the number of clients that can go to any facility. There is no capacity restriction. Okay, all right. Now, what were you suggesting? Yeah. What is the greedy algorithm for this? Say that again. Say it more clearly. Yeah.
So let's say
tell me which facility you'll pick first in your greedy algorithm.
Facility O.
Facility, okay.
So the C of O.
Okay.
C prime of O. We already have a C over there.
Right.
C prime of O is equal to C of O.
Right.
Plus something equal D J O.
What J's are you summing over? What are the J's you're summing over when you want to pick this facility? Everybody? J coming to that guy? But to begin with, you're the first facility. So what will be the J's you will sum over? Yeah?
Another method. First, I try to convert this problem to a set over problem.
Okay.
Which, I'll make those sets first.
Okay.
The way I make that is I select those lines which has the minimum distance to that set.
Okay.
So a particular factory has those set of lines.
Right.
Now,
But here's the problem. If without knowing who else is open, how will you know where a client gets assigned?
no, I'll choose that edge
Okay.
which is minimum to that factory. Because from one particular client, I can have multiple edges going to other factories.
Got it.
So I'll take that edge which has minimum distance.
Good. So let me understand your algorithm. Your idea is, for every client, find the closest facility. Okay? Assign the client only to the closest facility. That will automatically every client will now go to some facility. Okay? But in this method, all the facilities you've identified have to be open, no?
Not
Because everybody is going only to the closest facility. So you're not being greedy about it in any way. Of course, other than just going to the closest guy.
But that can happen. The cost to those edges can be more than the cost of opening those factories.
Exactly.
In that case,
Uh-huh.
this algorithm mine can be better than.
Okay, so, let me understand this, okay? So every client goes to the closest facility, okay? Okay? This doesn't seem like a great algorithm because, you see why, right? Do you see? Yeah, we are not controlling for which facilities are helping to cover a lot of people. I'll give you a small example. Suppose you have a facility location problem where all these guys are distance 1 from a facility. The facility cost is 1. Okay, these distances are 1. But let's say there is a special facility which is slightly farther from everyone, right? So all of you guys have their own dedicated facility. But there's one special facility which is distance 1 plus epsilon from all these guys. So your algorithm will pick these dedicated facilities, whereas, you should have really picked this guy. And by making the facility cost much higher, this can be made to fail in a very bad way.
So
Okay?
we're trying to mean that if a facility is open,
Yeah.
then we define the cost function in a different way than the facility is closed. Is that a way of doing it?
No, all I'm trying to point out is the cost that a facility incurs depends on which other facilities are open. Because only if you know the whole set F, O, can you figure out where J is going to. So that's the problem I'm trying to get you guys to break somehow. Yeah. Okay, yeah?
Initially, we start with means all the clients are dedicated to the first facility, and then on second iteration we reduce that set. We take out few. Means now we have two facilities. We see which are closest to each of us, and when we are dedicated to the second one, we remove it from the first one.
But that can fail also, right? Because if you...
But we will add the new cost function will be the cost of facility plus the cost of the edges distance.
Right, I think you are trying something like, let's go through the facilities in order, according to some order.
You can pick the minimum cost facility.
Minimum one?
First, pick the minimum one.
Okay.
And then start iterating and then start dividing it.
Okay, all right, let me just understand that algorithm. This one is gone. Okay, so we start by ordering the facilities in increasing order of cost. Okay, so C1 is smaller than C2, right? So we go in that order. So what do you do when you pick C1?
All the nodes which are nearer to C1,
Right, closer.
closest to C1 are picked up.
So these are the guys who consider C1 their closest facility.
And rest of them,
Right.
we have to check whether the cost to C2 will be less or C1.
Okay,
Then keep on taking it and iterating it.
but okay, I see there's a point. So here, for the other guys, I try to figure out whether they are closest to C2 or C.
C1, C2 can keep on iterating it till C1.
When will you assign the client for sure?
The least, when you get the least one. And maximize the cluster on C1 should have the client on C, that C should be maximum.
Okay.
And the distance should be less than rest.
But how are you controlling for the fact that you are opening a lot of facilities?
Only initially one and then the second, we have to decide the second one.
Okay,
And then we can go if there are, if it is more than the previous one,
right.
then go for the third one. Or if it is less, then only two you have to be satisfied.
I agree, but how do you control for the fact that in this way, you're not opening too many facilities? That's the problem I'm having, trying to pass. I see that you're saying, good, if I go to C2 and its cost is, if my distance to C2 is better than C3, that makes a case for opening facility 2. But what if that way you keep opening everybody and then you pay too much for opening? That's what I'm worried about. So again, let's go back to my theme, okay? Remember what I told you in the beginning of this lecture. What is the progress you are making? That's the question I want. So you had a suggestion, yeah.
So could we look at the cost of the facility divided by the distance from the client and
Which client?
from each client, and then sort them in this order. So supposing that there were say 5 and 10
Okay.
cost of the facilities,
Okay.
and then distances were say 10 and 20.
Okay. So 5 and 10.
No, not 10 and 20. Say 10 and 30.
10 and 30. For the same guy.
Yeah.
Okay, so for the same guy, I have 10 and 30, let's say.
So supposing in this case the ratio comes out to be half, and in this case comes out to be 1/3.
Half and 1/3, yeah.
Yeah, so I say that it is less costly for me to open a facility for this client to join it to facility with cost rate.
I'm a little worried. What if I made this 500 by 100? Or sorry, 500 by 1000? That's not good, right? You want the magnitude, not the ratio. So that also doesn't work. Okay, you have an idea.
So you have lengths of these edges.
I have length on the edges, right?
You just first pick the maximum length.
Okay.
So this is D. Now consider a ball of radius D.
Okay, ball of radius D.
Whoever comes in this
Distance D,
yeah,
good.
just assign to that facility.
Good.
Say now the maximum, I mean the second one, just the smaller one of that D. So this is D prime. Now consider the same to be D prime and do this.
Okay, which one will you take? Which D will you take?
No, so first I pick the maximum one. So there will be some edge who attains this thing. So I will assign.
Okay, so let me understand your method. You start by the pair facility client such that the distance is the largest.
Now I consider a ball of this radius.
Now if you consider a ball of this radius from that guy, you will get everybody by your definition. So what are you going to do after that? Okay, that's gone, none, that one? Okay.
All its uncovered
Clients, okay.
and then sort them in the increasing order of distance.
Okay.
And then check whether for each, so let them be C1 to CK.
Okay.
So check whether adding C1 to this facility.
Good.
So what would be the total cost if we add C1 to this facility?
Good.
L1 plus
Good.
the
What is the ratio you're getting after? I just want you to think about, remember this ratio lemma in set cover, right? What is the ratio lemma we are after? You're getting there. I just want you to think about how you get there. Yeah, yeah.
say at some point in the set of facilities that have already been opened.
Good.
Say the last facility is open to say X.
Okay. And they've already covered some people or not?
Yeah.
Okay. So I've opened some facilities and I've covered some people. This is the state and the greedy algorithm. Okay. At state I have taken facilities F1 through Fi. And I've covered some set of clients. There is some set of uncovered clients called that UI.
So now for a particular client in the set UI,
Right.
what I want to look at is say it has distances D1 and D2 from facility.
Right. So F1 and F2, the guys before.
Yeah.
Okay.
They will also have some distances.
Right.
Those are D1 and D2.
Right.
And the remaining facilities that are there, they also have some opening for say C.
Right. Okay.
So what I want to look at is say among the remaining facilities, say C3 is the cost for opening the facility. So C3 plus D3.
Uh-huh. Okay, so let me ask again. What is it that you're making progress with? When you pick the next facility, think of set cover, okay? What did you do in set cover? At step Fi, you pick the set Si plus 1, okay? And how did you pick the set Si plus 1? Cost of the set divided by what? Number of elements it covers. And I was able to show for that set cover, I'll come back to this later, okay? I was able to show in set cover the ratio greedy step. was that the cost of the set Si divided by the number that it covers now is at most opt divided by everything, right? How did I prove that? You remember? Right? I took the optimal solution, right? I took the optimal solution and then I looked at how it covers everybody who's left and then I did an averaging, right? So I said this guy's ratio is C1 divided by 2. This guy's is C2 divided by 4. C3 divided by 3. Then I know that if I sum all these C's, I get opt. And I know if I sum all of these guys, I get at least UI because it does the job. Okay? Now I have to do something like that there. What am I using? Right? Yes, Ravi.
So am I allowed to
Yes, please, yeah.
take the cost of each facility?
Good, cost of each facility.
Denominator is the saving in cost of servicing. I didn't know this.
Savings in what?
In cost of servicing all the clients.
Oh, so you're doing savings in the cost. Okay, I see. Wow. It's possible. I don't know how to analyze that. Okay.
I think it should be true that some of those savings is
At least,
at most,
at most.
the total savings to the all.
What do you mean by savings? You mean new people you're...
And I see how much I reduce the cost of existing clients and the new clients.
Ah, okay. So let me understand this algorithm, okay? So I think Ravi's algorithm is... Yeah. Okay, so let me understand if this is your algorithm. Let's say you start with F1. Okay? So first F1 is your only open facility. So that means everybody has to be served by that guy, right? So you make everybody be served by that guy. I think what Ravi is proposing is pick F2 so that if you put F2, you have to pay C of F2. But you will get savings in these costs. Some of them, I think it's sort of like your old algorithm, right? You're saying, I don't need that guy, I don't need this guy, now he can go here. The savings is the difference in the length between this and that. This and that. That's what you're thinking of, right? Yeah. I don't know how to analyze this.
But if you sum up the savings cost per each facility,
Right.
that is most.
See, the problem is you don't know what your initial hit is. Because with F1,
Compare it all. Compare it to how much opt saves over the initial versus what you say.
right. So yeah, so this it's okay. This is a good suggestion, but I don't know how to analyze it yet. But I'm looking for something very simple, like what was the progress I was making? I just got more uncovered guys. Let me just figure out when I put in a facility who I will cover, because that's the problem. All of you are trying things where I used to be covered there, now I'm going to be covered here. How much am I saving? Just figure out who you want to cover right away, and then be done with it. Okay? Yeah, you have a suggestion. I'll come back. Yeah. Cost per unit distance? Okay. Clients you're covering. Okay. Good. Okay. So tell me what it is. So suppose I have F and it's covering clients 1, 2, and 3. What will be the ratio I'll put? So D1F, D2F, like this? But this doesn't sound right, because if D is very large, you don't want to pick this facility. Right? You see, if D is very large, you will end up picking this. So it's actually in the wrong direction somehow, right? So again, think, how do I use opt to induce something of good ratio? How do I prove a lemma like this? What should UI be? That's the first question.
For each of the factories in facility,
Yeah.
we have a cost of the facility plus the distance. So if there are any clients,
Yeah.
take the summation into the cost, and then summation of the distance into the cost, and by the number of clients it has.
Good. So what is UI?
So UI is the number of clients which are not served here.
Good. That's it. That's what I was looking for. Okay, so let's try that, okay? So UI is the number of unserved clients at beginning of I. Okay, so to begin with, U1 is all the clients. Okay, so I want to pick a facility and some clients, I don't know who, but I'm going to pick some guys, and I'm going to get a ratio where the denominator is going to be the number that I'm going to serve right now. Okay, and I want it to be so that the cost I pay, so cost paid at step I, divided by number covered at I, right? This is the number of guys I want to now, is less than or equal to what? Cost of opt divided by number of uncovered guys. This is what I want. Okay, now what is the cost of opt? It's got two parts in it. It's got facility you're opening and distances. So clearly the numerator has both of them in it. So definitely what I'm paying at time I should be cost of the facility I opened at time I plus sum over clients I assign now. Okay, whoever they are, let's say J belonging to covered at time I, distance from J to F. Right? And what should be the denominator? Is the number I cover at I, which will be size of covered at I. Okay, this is the ratio I want. Okay?
Question. In this, which function, which facility is serving which clients? How do you assign that?
That's the question. Now we have to look at opt and figure it out. This is the whole point of the decomposition lemma. Like in Christofides, right? You looked at opt and you said, hey, there are like two matchings. Like that you have to do something here. That's what I'm trying to get you to think. What is it? What is it about this set you can prove so that you can get this ratio lemma to work? Okay, let's look at opt. Okay, let's do what opt does. Okay, so here is UI, okay, uncovered. Let's look at opt. Okay, opt has some set of facilities. Okay, it may even have some facility that you picked. Okay, and opt itself has a way of covering everybody. This you've already done, by the way. Okay, how does opt cover everybody? Well, once you tell me who opt is, everybody will go to their closest facility, right? In opt. Something like that. Right? Now, look at for each facility in opt, right, that covers somebody in UI, what its ratio is. Okay, well, this is, let's say opt has 1, 3, 7, 9, okay, facilities. So opt paid cost of facility 1 and it paid cost of connecting one to this client. That's how opt covered the client. Okay, opt paid 7 and it paid the cost of connecting these two clients. Right? So you write each of them for opt. Okay, what does it look like? Okay, C of 1 plus distance from 1 to whoever it covers, you know. I put some numbers here. This is 10, 11, 12, 13, right? So distance 1 to 10, right? When opt did that, when opt opened 1 and covered client 10, how much did it help you reduce the number of uncovered clients? 1. So that's the ops ratio for that set. Let's try this set 9. Okay, let's say it goes to clients 20 and 21. Opt paid cost of 9 and it paid distance from 9 to 20, distance from 9 to 21. How much did it reduce the number of clients by? 2, right? Good. Excellent. If you sum all these numerators, what do you get? Cost of opt. Sorry, that's my phone. Right? So you get cost of opt, okay? But if you sum all the denominators, what do you get? UI. Great. So we got exactly what we want on the right hand side. Okay? So if you picked any one of them, okay, and you just figured out whoever has the best value of this ratio, right? It's less than or equal to ops ratio. Now comes the very last question. How do you pick a facility which has the best ratio? Well, it's staring at your face. pick the facility such that among the unserved clients, it has to minimize the ratio of the cost of the facility plus the cost of the assignments divided by number of guys you cover. Okay, how do you figure out which one of them is, how do you figure out which facility and which set of clients it covers minimizes this ratio? I need to figure out what this set is, right? But now you think a little bit carefully, right? Ravi knows the answer, right? A lot of people now know the answer, right? So basically, when I look at a particular facility, right? Exactly. Because you're already paying the dead weight of the facility cost. Now you want to start covering more people. Which people would you cover so that this ratio is as small as possible? The first guy you pick should be the closest guy to you. Now we'll come back to your idea. Okay? The second guy you pick should be the second closest guy to you. So finally, the facility which gives you the best ratio is the one that minimizes, you take the facility, pay the cost, you sort everybody in increasing distance from it in UI. Okay? And you take every possible prefix. So if you take the prefix of the first guy, you will pay cost of this facility plus this distance divided by 1. If you take this prefix, you will pay cost of the facility plus this distance divided by 2. Clearly, one of those prefixes is going to give you the minimum ratio for this facility. Try it with all the other facilities. Pick the one which minimizes the ratio. And I've just given you a proof that it's at most ops ratio. Plug and chug, you get log of number of clients approximation.
So by doing this,
Yeah.
suppose consider the viewpoint of a client.
Yeah.
The client has many servers as well.
Right.
And one of them is the closest server.
That's right.
But if I do this,
Right.
there's a possibility that it might not be connected.
Absolutely. Yeah, absolutely. So another way now do you understand this, right? If you understand this, what we are doing is actually a set covering problem. Our sets are basically these kind of things. Our sets are facilities and some subset of clients they serve. How many possible sets are there? Exponential number. Every possible subset of clients can be associated with the facility. What we have done is come up with a clever way to find the best ratio set involving every facility for a particular UI. Right? Just by doing this prefix sorting. Now you can figure out, so this is the reverse engineering you have to do to design an approximation algorithm. Take opt, look at what opt is doing for you in terms of ratio, then use that to figure out what you should do. And then see if you can do it. Sometimes you can, sometimes you cannot. Sometimes searching over an exponential neighborhood is not possible. You have to do some approximation even there. Yeah.
In the set coverage,
Yeah.
take an element
Right.
and see a feasible solution.
Right.
That element can get covered with many sets.
That's right.
But here, one client in the feasible solution is
Right.
covered with only one.
That's because getting it covered by 2 people is wasteful. Yeah, exactly.
Sort of partition will come.
Exactly, yeah. I mean, in this problem, making a client be covered by more than one facility is wasteful. Yeah. So you won't do that. Yeah.
So this algorithm, why will every client get covered?
Why will every client get covered? Because as long as UI is not empty, you will continue doing this.
So then we stop adding CFI after some point. We will not add CFI again because we have to, because it's possible that they open every facility
I see.
and still some clients are there.
That's right. So for example, this analysis tells you, even if you pay for CFI every time you pick it, you're still within log n of optimal. That's what it says. Yeah, you're right. So this is a subtle point, okay? In the first step, I may have picked facility 1 and covered clients 1 to 10. In step 20, the best ratio facility may still be facility 1, covering clients 100 to 110. This analysis says you can pay for the cost of 1 again in the 20th step, and still you'll be within log n. But actually, you don't have to include it, right? This analysis says you can include it and it'll still give it to you. Yeah, good point. Okay, so this is the log D approximation for uncapacitated facility location when the costs of connection are arbitrary. But if the costs of connection are a metric, like in the example I showed you, right? You know this, right? You can do much better than log. You can actually do something like a 3 approximation. That will show you day after tomorrow. Okay? But this is for the non-metric UFL, which is the one we just tackled, right? The cost don't obey triangle inequality. You can't do better than log. That's because non-metric UFL is essentially like set cover. You can take a set cover problem and encode it as UFL. Okay? And then doing better than log n for this version of facility location would be improving the log n for set cover, which by now it's known as NP hard. Okay, so that log n algorithm, except for a constant factor, you cannot improve. So this is the best possible within constant factors approximation algorithm for this problem. And this is due to Dorit Hogbaum. She wrote a paper about it many years ago. Yeah. Okay, so let's do the second problem. Yeah. Second problem is it's also equally tricky, maybe more. Yeah. Okay, second problem is generalized Steiner Forest. And you have to tell me what UI is. That's the main point. Okay, so remember what an active component is. An active component is a set which has a pair which is missing its mate. So its intersection with SITI for some I is exactly 1. That means it's got an unconnected pair. Okay? So the gluttonous algorithm just picks the closest active pair, okay, merges them, and it continues. I'm sorry, I'll take this. Okay. Probably those guys. Think about this. Suppose there is this pair, okay, and there is this guy is also the triangle pair. Okay, so the number of active components is this guy, and this guy. And you're saying if I pick this, then this thing also stays active. Right? Because I still haven't found the mate for the triangle. So here actually the number of active components goes down by only 1. That's why dividing by 2 and all is not really that important. But does this answer what you were asking? Yeah. Okay, so the algorithm, if it finds this path, it will form a bigger component, but it will still be active because the triangle hasn't found its pair. Okay, so what should be the ratio lemma? Let's write the ratio lemma. Cost of opt divided by UI. That's what I want. Yes? What I am doing is adding a path, right? Okay? In the best case, by adding a path, how much am I decreasing the number of active components by? By at least 1. At least 1. This is the important point. Right? Because you started with 2 endpoints which were active. In the worst case, after this, like in this example, after you merge them, it is still active. But the number of components has gone down by 1. So this decrease is 1. That's like covering. Okay? So what I want to prove is my cost divided by my decrease is related to ops cost divided by somehow ops total decrease. Can I prove something like this? That's the question. Yeah, wrong argument is good. Yeah.
So think of these active components as big vertices.
Okay, they are big super nodes. Okay, like these. Yeah.
Now, opt must have used at least UI pass between them. Because opt corrected all of which are missing.
Shit. Why should it have used at least UI between them?
It must have at least UI by 2 between at least half of them because it made paths. So it at least joined the players, right? So or must have used at least UI by 2 paths between them.
UI by 2, I agree, yes, yeah. Because see, opt cannot leave each of these components as a component by itself. Because opt also has to connect this triangle to somebody. Right? So opt has to at least get out of each of these components. You don't exactly know how it gets out, but it needs to get out. Because otherwise these guys will stay active. Okay?
Now see that I use the cheapest path.
Okay.
So my path should be at most opt divided by UI by 2.
That's roughly right. That's roughly right. But
The problem is that
what is the problem? Yeah.
that opt will be using a path which does not consist of whose endpoints are not the terminals. Opt will be using because when we add a path, we opt at pin 2 terminals.
Right.
But opt path may not be of that type.
That's exactly right. So what we need is a decomposition lemma. Always we need decomposition, right? So what is it we need to decompose into? Always it starts like this, right? Consider opt. Remember the whole point of today's and tomorrow's lecture is how you bound it is using opt. So consider opt, and this is what you are doing. You're saying, look at how opt repairs all these guys. Opt needs to connect the triangles together. Opt needs to connect the squares together. Okay? So consider opt. Opt, if you add it to your current components, will have the property that when you add the edges of opt, the connected components will all be not active, right? Because it's supposed to kill everybody, right? I mean, if they're active, right? So look at how opt connects all your current active components. Okay, that's the first step. Okay, so I'll draw a better picture of that. Look at opt. First of all, remember my components are already in this big, right? I've already done some connections here. They're all active, okay? Opt will connect them up in some way. In fact, it may not connect them in one tree. Remember that. Because opt is a forest. Okay? Now, I need to decompose opt. I need to break up opt into parts, just like I did in my UFL, right? I took it into different parts, such that each part will help me reduce this UI by a little bit. That's what you were trying. But the parts are all disjoint from each other, so that I don't land up overcharging opt. I'll tell you what I mean. For example, if opt looks like this, right? These are all active. Right? One way for me to decompose this is say, pair this guy with that guy. Pair this guy with this guy. Pair this guy with this guy on opt. But look, these paths are overusing the edges of opt many, many times. I don't want to do that. Right? You see the problem, right? This would not be a decomposition. So how would I make this a good decomposition? Right. Find the shortest two active guys in opt's tree. Take that. Why is that ratio as good as this? Good. How will you do that with this tree? I need to break this tree up. Let's make a... So there are lots of guys here. Okay? And these guys are all pairs of each other. Okay? I need to break this tree up. Who are the active components here? These guys, right? These are the active components. They have not found their mate yet. How will I decompose this tree into parts, right, which are disjoint from each other, and together basically connect up every active component with some other active component? Yeah.
So once an edge is used, we can update it. So we can update it way to 0 so that it's no problem.
That's the same as saying decomposition, right? Because if I use this part, it's gone. Right.
So I will use the long edge only once.
I want to use, if possible, I want to use every edge only once.
Can we replace it with multiple edge with its weight adjusted fraction, the number of times?
It doesn't help somehow. Yeah, I mean, if this edge is length 100, you can't replace it with 100 edges. That's wrong. Because when I go from this node to this node, I have to pay 100 in the length. That's not right. So there's actually two fixes for this. Yeah. Right. Right. Okay. That's what the algorithm is doing, I agree. But I have to pay for it. Okay, but there's a problem with that, because if I find the shortest path between here, opt3 will use this, right? If I contract, I may not necessarily use opt's path in my algorithm. Okay. Okay, you're getting close to there. Yeah. Basically, so let me add one more idea. I think I'm making it maybe too difficult. Okay. I don't have to use one copy of opt. If I want, I can use 2 copies of opt. Remember how we started today? We took a tree. What did we do with it? Doubled it, right? Chalo, let's double this. Instead of using one opt, I'm going to use 2 opt. Okay. Now can you see how I can match up every active component with some other component? Shortcut. Take your Euler tour walk. So this walk will pay for this pair. This walk will pay for that pair. This walk will pay for that pair. So by doubling opt, you get a cycle. And the cycle is 2 matchings. Pick any edge in any of those matchings, right? It actually reduces the number of active components by 1. But in sum, all of those matchings reduce the number of active components by UI. How much have you used? 2 times opt. Okay? So instead of decomposing 1 times opt, if I decompose 2 times opt, I can think of 2 times opt as a sum of 2 sets of shortest paths. Or if you like, just sets of shortest paths from each active component to the next one in the Euler tool. Okay? We have to use metric property. That's absolutely right. But we already argued, right, that you can assume it's metric without loss of generality. Because if my direct edge to you is much costlier than a path, why would I ever use a direct edge? I'm just trying to connect to you. I'll just choose the shortest path. So that's not a problem. Okay? So the short of it is, take opt, double it, then shortcut it. What you get is a cycle between the active components in opt. You may get many cycles, by the way. Right? Each of the paths in the cycle is a feasible path you could have picked and reduce the number of active components by 1. The sum of those paths is 2 times opt. And the amount of reduction they give is exactly UI. Because each path, right, if there's 3 guys, I have 3 paths here. So I've reduced by 3. So I've proved my lemma. So I get a 2 ln number of terminals, right? Number of active components used to be number of terminals. I've got myself a 2 ln R approximation. Okay? So again, just like for metric UFL, we can give a 3 approximation. For this problem, we can give a 2 approximation, which we'll do day after tomorrow. I guess everything is going to day after tomorrow. It can't be right. So maybe 4th day, yeah, something like that. Yeah. Okay? So these are the 2 problems we'll come back to again. But your main idea is, when you want to be greedy about a problem, right? You actually don't even know what you want to be greedy about. Right? If you want to prove a guarantee. The way you want to figure out what you want to be greedy about will involve looking at opt, breaking opt or many times opt, 2 times, 3 times opt into pieces, so that those pieces you can find easily, efficiently, like a path or a facility, and you can reduce somehow the work you have to do at each step. Okay? There are a lot more examples like this, but I think you get the idea. So tomorrow, I'm going to tell you about local search. Okay? I'll give you 1 or 2 examples. Then I'll tell you a little bit about LPs, and then we'll go directly to LP rounding. Okay? If you have never seen linear programming before, it's a good idea to go and read about what basic linear programming is. Probably even Wikipedia will do. It's a good start. Okay? So just go to Wikipedia, read about what linear programming is. Because that's coming up tomorrow, and definitely day after tomorrow we're going to do linear programming. But tomorrow I'll show you 2 examples of local search, and I'll also show you, I don't think I'll have time to do dynamic programming, the rate I'm going, but we are in good enough shape. Yeah. Okay, we'll stop here. See you.